Okay, we're going to continue and complete section 6.4, which is on sum and difference identities. I have nothing new to teach you to start. I just didn't want to have to overwhelm you last class, so we're ready to start with this first questions here, first two questions. We're going to prove a couple identities, and we're going to use these identities to prove these identities. So we want to prove that sine pi over 4 plus x plus sine pi over 4 minus x equals the square root of 2 cosine of x. And we're going to use these sum and difference identities in order to do that. Well, hopefully what you can spot here is that you have a sum identity right there, and you have a difference identity right there that you can use. So if we look at the yellow highlight, we have a sum identity. We have a sine a plus b. Sine a plus b is this one up here. We're going to do sine a cos b plus cos a sine b. Sine a is pi over 4. Cos b is cos x. I got to take another look. Sine a cos b plus cos a sine b plus cos a sine b, which is x. So all this in red is the yellow highlighted part. Now we hit the plus sign, so I put plus. Now I'm ready to do the green highlighted part. This is going to be a difference identity. It's sine a minus b. So that's this one this time. So we're going sine a cos b minus cos a sine b. It's exactly the same as the one above, except that minus sign. Okay, so I can do this quite quickly. It is sine pi over 4 cos x, but now it's going to be minus cos pi over 4 sine x. Okay, and just like when we work with identities before, we're just going to work on the one side for now, so we're not going to deal with this root 2 cos x. We're going to try to turn this left-hand side into that. Notice anything now that you have this 4 little different sections here? You've got this piece, one term there, one term there, one term there, and one term there. And hopefully what you notice, and you're very pleased with, is that this term cos pi over 4 sine x and this term cos pi over 4 sine x, you can cancel because this is take away, this is add, so it's a positive one, a negative one. They're gone. The only thing you have left is sine pi over 4 cos x plus sine pi over 4 cos x. Oh, you've got two of them. So you have 2 sine pi over 4 cosine of x. Wow, we've come a long way. Let's see if we can finish this off. Now, sine pi over 4, this piece right here, we know what sine pi over 4 is. Think back to the unit circle. Sine pi over 4 is root 2 over 2. And then we still have the cosine x. Hey, look, when we multiply this 2 times root 2 over 2, we can cancel that. We are left with root 2 times cosine x. That is exactly what we had up here. We have the same thing. We have solved this thing. Yay! Okay, next one. We're going to solve tan a minus b equals tan a minus b divided by 1 plus tan a tan b. This might seem familiar to you because if you look, that's exactly this right here. Oh my gosh, so is it done? We're finished. It's no. Okay, what I'm asking you to do here is pretend that we didn't know this identity here. I want you to prove this identity by using these ones over here. How are we going to do that? Well, I know I said usually you're going to start with the more complicated side, and you'd think you're probably going to start over here, but I don't think there's much you can do there. But if you look on the left-hand side, you can do something. Because tan a minus b, what's tan the same as? Tan's the same as sine over cos. So tan a minus b is the same as sine a minus b divided by cos a minus b. Hey, look what we have here. We have two difference identities. So let's figure out what they equal. Let's start with the sine a minus b. Sine a minus b, we're literally going to write down this right-hand side right there. So it's, I hate it when it does this. It's sine a cos b minus cos a sine b. All divided by, now we got to look up cosine a minus b. I don't think we've used this one yet. This is this one down here. So we're going to write down Cos A cos B plus sine A sine B. Cos A cos B plus sine A sine B. Okay, now how did that help us? First of all, there's no canceling you can do here. I know some people might be saying, hey, I can cancel those cos B's and these sine B's. You can't do that. This is a binomial. There's a minus sign. This is a binomial. There's a plus sign. You have to have exactly the same thing. So let's compare this huge mess here to what we want to end up with. You see how we have two terms on the top, two terms on the top here, two terms on the bottom, two terms on the bottom here. Okay, this is a hint for you that you probably want to turn this first term into tan A. Wow, how are we going to do that? This term into tan B. Sounds difficult. This fourth term over here, sine A sine B, we've got to turn it into tan A tan B. That seems really hard. And this term, this cos A cos B, we have to turn that into 1. Now that's something that we can actually figure out. How do we turn anything into 1? If you want to turn 5 into 1, if you want to turn 5 into 1, what do you do to 5? Divide it by 5. If you want to turn m into 1, what do you do? Divide it by m. If we want to turn this term, if we want to change this term into 1, why don't we divide it by itself? Now we can only do that though if we divide everything by that amount. So let's do that. We are going to write down the same thing, sine A cos B, but we're going to divide that by cos A cos B. Minus, the next term there is cos A sine B. What are we dividing it by? Same thing, cos A cos B. All over, on the bottom we have cos A cos B. What are we dividing that by? Cos A cos B. We're dividing everything by cos A cos B. Plus sine A sine B. What are we dividing that by? Cosine A cosine B. What a mess. But look at what starts happening now. In this term, now you can start canceling. This is one term, this is one term. You can cancel those out. Over here, cancel it out. Cancel out and cancel out. And that's it. But let's take a look at what's left here. What's left in this first term is sine A divided by cos A. What's sine over cos equal? Tan. So we have tan A, just like we wanted, minus, what's left here is sine over cos again. We have tan B, just like we wanted. When all this cancels, what's left? You do have something left. You have 1. That's what we wanted to turn it into. We did it. Okay, now, we're not going to divide sine A sine B by cos A cos B. I mean, you are, but what you probably want to think of it is, I'm dividing sine A by cos A. We can kind of cancel those, because sine A over cos A is tan A. And I'm going to divide sine B by cos B, and sine over cos is tan B. Look what we have done. We have changed it exactly into what we wanted. It's almost magic. I think that is so satisfying. I love that question. Okay, here's the new stuff. We have 2 new sets of identities. I've listed them here for you. You don't have to write them down. Yay. We have odd-even identities and cofunction identities. The reason they're called odd-even, it's not really that important. It has to do whether the function is symmetrical around the y-axis. And in other words, when you flip it over reflect it over the y-axis, does it look the same? And it turns out that cosine and secant looks the same. You can think back about that. Think of the mother function of cosine. If you were to reflect it over the y-axis, it looks exactly the same. Anyway, don't worry about that. It doesn't really matter. But cosine and secant are the even ones, and these other ones are the odd ones. Okay, so what you'll notice here is that sine negative A equals negative sine A. So, for example, if you wanted to know what sine negative 30 is, well, sine negative 30 is the same as sine 330 degrees, isn't it? And what is sine of 330 degrees? Well, that's in the 4th quadrant down here, and sine's negative down there. So you know it's going to be a negative answer. And the reference angle is 30. What's sine 30? 1/2. The answer is negative 1/2. What this identity is telling us is, another way we could have done that is, you could have just said, oh, if it's sine negative an angle, it's the same as negative sine of an angle. What's sine 30? 1/2. And negative, slap a negative on it, you get negative 1/2. That's negative 1/2. Right? It works. And this works for whatever angle, whether it's a reference angle, angle bigger than 180, bigger than 360, it doesn't matter. It will always work. And that's the same for cosecants like that, cotans like that, tans like that. But cosine and secant are a little bit different. So let's look at cosine for a second. Let's say we were doing cosine of negative 60 degrees. Well, cosine of negative 60 is the same as the cosine of 300, isn't it? And what is the cosine of 300? Well, that puts us down in this quadrant again, and down in the fourth quadrant cosine is positive this time. The reference angle would be 60. Cosine of 60 is 1/2, and we already said it would be positive, so it would equal 1/2. But what this identity tells us is a faster way to do that is if you have cosine of a negative angle, it's the same as cosine of the positive angle. Hey, that's pretty useful. Cosine of 60 is 1/2. We're finished already. Okay, those are your odd and even identities. For the cofunction identities, we talked about this a little bit before. This is the reason why there's sine and there's cosine. There's tan and there's cotan. There's secant and there's cosecant. The co refers to complementary, and complementary angles add to 90. So basically what this is saying is if you have some angle like sine 40 degrees, whatever that equals is exactly the same as what cosine equals for 50 degrees. Those two angles are complementary, and sine and cos are the same for the complementary angles. Same with tan. If you had tan 82 degrees, that's going to be the same as cotan of 8 degrees. Those are the complementary angle. So sine and cos go together, tan and cotan go together, and secant and cosecant go together. So whatever the secant is of 20 degrees is exactly what the cosecant is of 70 degrees. That's what the cofunction identities are showing you. Alright, so let's try some of these. We're going to find the exact value of the following. We did this sort of thing last day. I've just put some negatives in this time. So first of all, we can use one of the odd-even identities. If it's sine of negative 7 pi over 12, that's the same as what? Well, we use this identity right here. It's the same as negative sine 7 pi over 12. So we don't have to worry about that negative anymore. We'll just slap a negative on at the end. Now, same as last time, I'm horrible at doing this in radians, so I'm going to convert 7 pi over 12 into degrees. Multiply by pi, 180 over pi. So pi's are gone. 12 goes into 180 15 times. 7 times 15 is 105 degrees. So what I need to figure out is what's negative sine of 105 degrees. Well, 105 is not a special angle. It's not on our unit circle. So this is where you're going to have to use one of the identities from last day. 105 is the same as 60 plus 45. We could do it that way. Why don't we do that? We'll do 60 degrees plus 45 degrees. So now what you have to do is you have to use one of the additive identities, which I have written here again. So we're using sine a plus b. Remember this negative, we're just going to hold that out front. I'll just put it in a square bracket. So it's sine a plus b, which is the top one. It's sine a cos b plus cos a sine b. Sine a is sine 60. Cos b is cos 45 plus cos A is cos 60, sine B is sine 45. Squish it in there. Okay, so we have negative. Now, we know some of these. Sine 60, we know it's root 3 over 2. Cos 45 is root 2 over 2. Plus, there's a plus sign. Cos 60 is 1/2. Sine 45 is root 2 over 2. So that equals negative root 3 times root 2 is root 6. 2 times 2 is 4. Plus 1 times root 2 is root 2. 2 times 2 is 4. Hey, we can get the same denominator here. So here's some different ways you could write this. One way you could write this is negative root 6 plus root 2 all over 4. You could just put the negative out front like that. If you do that, that's exactly the same. If you put the negative up front, it's the same as negative root 6 plus root 2 all over 4. But if you're going to put that negative up into the numerator, you have to do one of two things. You have to either put this in brackets, or if you don't want to put it in brackets, you have to expand that negative 1, do mountains with the negative there. So it'd be negative root 6 minus root 2 all over 4. One of these three answers is acceptable, but this is not acceptable. You couldn't have negative root 6 plus 2 root 2 all over 4. That's wrong. Either put the negative out front or put this in brackets if you're going to put the negative up there. Okay, let me get rid of this because we're going to need all the space we can get to solve the next question. Got to get the exact value of the secant of negative 15 degrees. Well, let's start up here and look at secant, and we see that the secant of a negative angle is equal to just the positive secant of the positive angle. This is great. So in fact, our question that we're solving becomes just secant of 15 degrees. Okay, next thing. Secant is really tough on the unit circle and stuff, but what is secant? It's the reciprocal of cosine. So if we take the reciprocal of cosine 15, we'll be in business. Next thing, 15 is not one of our special angles. How could we get 15 degrees? How about 45 degrees take away 30 degrees? That'll work. Okay, so we have 1 over, this is a difference identity, cos A minus B. Cos A minus B. So it's this one again. Cos A, cos B plus sine A, sine B. So cos A is cos 45, cos B is cos 30, plus sine 45, sine 30. Sorry, this is so squished. Equals. Okay, now we can figure out what all those things equal. Cos 45 is root 2 over 2. Cos 30 is root 3 over 2. Plus sine 45 is root 2 over 2. Sine 30 is 1/2. Okay, we have 1 over root 2 times root 3 is root 6 all over 4. Root 6 over 4 plus root 2 over 4. So we end up with 1 over root 6 plus root 2 all over 4. 1 over means the same as reciprocal. Or if you want, the other way we can think of it is 1 over 1 divided by all this, and when you divide, you actually flip it and multiply. Either way you think of it, you're going to get 4 over root 6 plus root 2. We're very close to being done, but we like to rationalize that denominator. So we're going to multiply this denominator by its conjugate, root 6 minus root 2, and what you do to the bottom, you got to do the top. Okay, on the top, let's not multiply through. Don't do mountains. Just keep it like this because I think that 4 is going to cancel out. On the bottom, root 6 times root 6 is 6. The next two terms will cancel out, right? Root 6 times negative root 2 is a negative root 12. Positive root 2 times positive root 6 is a positive root 12. Those cancel out. And root 2 times negative root 2 is negative 2. So you end up with 4 root 6 minus root 2 all over 4. Just like I thought. Those 4's cancel, and our final answer, squished in the corner here, is root 6 minus root 2. Final answer and exact answer for how much the secant of negative 15 degrees is. Alright, last one. Whoa, does that look ugly? We're going to start using these identities up here. So we have cosecant of a negative angle. Cosecant of a negative angle is equal to negative the cosecant of that angle. So we can move that negative up front. We have negative cosecant of x. Sine of pi over 2 minus x. So that's right here. It equals cosine x. Cosine x. Put it times dot there if you want. Now this, secant squared pi over 2 minus x. Okay, if you look up here, secant pi over 2 minus x is just cosecant x. So it would be cosecant x. But look at, this is squared, so it's actually cosecant squared x. And then we have that minus 1. Unfortunately, we can't cancel the cosecants because this is a binomial on the bottom. In fact, you have to notice something about this denominator here. You have to think all the way back to the very first section in chapter 6 when we did Pythagorean identities. And one of the identities we did looked like this. I will write it over here. 1 plus cotan squared of an angle equals cosecant squared of an angle. So if you compare that to this denominator, you see it's almost the same thing. In fact, if we move this 1 over, so left the cotan squared theta, and brought the 1 over, it would now become minus 1. This piece here is exactly the same as the denominator, which means we can replace the denominator with cotan squared theta. It's exactly equal to that. So we have in the denominator cotan squared theta. In the numerator, this cosecant, I don't like it. Let's switch it into either sine or cos. What's cosecant the same as? It's the same as 1 over sine. Oh, by the way, this should be x, not theta, because we're talking about x's in this question. So 1 over sine x times cosine of x. So in the numerator, if you just look at this piece up here, all there, you can multiply those two things together. 1 times cosine x is cosine x. Have the negative sign still, don't lose that. All over sine x. That's the numerator. And what's in the denominator is cotan squared x. Okay, still looking in that numerator. Still look right up here. What does that equal? Cosine x divided by sine x. That sounds familiar. That's one of our basic ratios. That is cotan. So we have negative cotan x over cotan squared x. Hey, we got one cotan here, two cotans here. Let's cancel them out. You're left with 1 on the bottom, cotan x, and we still have a negative 1 on the top. 1 over cotan x, that's the reciprocal of cotan. What's the reciprocal of cotan? Tan. And we still have our negative. Believe it or not, this messy thing we started with up here simplifies to negative tan x. That's the sort of work you got to do today. Hope you enjoy it, people.
You tell no more candy.